In this lecture, we're going to talk about the relationship that exists among our three elastic constants that we know about so far: the modulus of elasticity E, the shear modulus G, and Poisson's ratio. Now let's talk about these real quick and as a review as to what they are. We know that if we have a stress-strain curve, a tensile stress-strain curve of a material, where we have sigma and epsilon, the axial stress and strain, the slope of that line would be the modulus of elasticity E. If we have a shear stress-strain curve, tau and gamma, the slope of that line in the under the proportional limit stress will be the shear modulus G, and Poisson's ratio is defined in the elastic range as minus the transverse strain divided by the axial strain in a tension test. So again, in a tension test, we have a state of stress that is pure uniaxial, but we develop strains that are axial and transverse. Now I'm drawing these arrows coming out this way, but the transverse strain is equal to minus nu times x epsilon axial. We also get a strain through the radial direction of the bar as well, coming out of the page at us. Well, simply stated, the relationship among the elastic constants is G is equal to E over 2 divided by 1 plus nu. We're going to go through and show where this comes from in a little bit. There are some restrictions to using this formula, however. We need to have what's called an isotropic material. The prefix iso means the same, tropic means direction. We need a material that behaves the same in every direction. Or approximately so. Now, a lot of materials behave differently depending on the length scale that you look at them. A lot of polycrystalline metals, if you look at a region of several grains of the metal, steel, aluminum, whatever, can act as an isotropic material. They can behave the same if you pull them up and down or left and right, and so forth. If you look at the individual crystal level, a lot of those materials are what is known as anisotropic. That means that they do not behave the same in every direction. If you heavily process a material like an aluminum alloy, you can elongate grains and you can develop what's called texture anisotropy. In this case, this relationship would not apply. But in a lot of cases, and the ones that we're going to look at in our course, we will primarily be looking at isotropic materials, things like metals, glass, that we're at such a length scale that if you pull on it up and down or left and right, you'll get the same kind of stress-strain response. Some very important classes of materials are anisotropic. These include composite materials, where, for example, in the fiber direction of the composite, you have a lot stronger or stiffer behavior than you do if you pull on this fiber and glue system perpendicular to the fiber direction. So, just want to make sure we understand what our assumptions are when we're involved with isotropic materials. Now, the reason why this formula is going to be important, and in my class, I will never ask you to memorize this. I will give it to you if you need it. But the reason why this is important is that in a lot of material property tables, you will see the modulus of elasticity E and Poisson's ratio nu listed, and you will be expected to calculate the shear modulus E. So let's write that down. Again, if you calculate G this way, you're making the assumption that your material is what's known as isotropic. All right, so let's see where we can get this. And it's kind of a neat application of stresses on an inclined plane, which we talked about not too long ago. Let me clear off a new page. And so I have my axially loaded bar, and I'm going to draw a square on the surface of this bar. Let me put it in a different color. And I'm going to align the square with the sides of the bar like this. And inside of that, I'm going to draw another square, but one that's tilted at a 45-degree angle. I'm going to draw this square on the material before the load is applied so that all these angles are nice and square right angles. The dimensions of this are perfectly square. I'm going to draw this square out outside of this so we can visualize this a little bit before and after the deformation. So here it is again. I'm just going to draw this before it's deformed. Now the square is going to stretch out because we're applying an axial force to it. It's also going to get a little bit shorter in the transverse dimension because of Poisson's ratio. So this turns into a rectangle. And I'm going to exaggerate these quite a lot. Okay, so it gets longer and it gets shorter. Similarly, the square that's been tilted at a 45-degree angle where it's lined up with the middle of the sides of that red square becomes more of a diamond shape. Okay, just like that. So before it's loaded, we can say that this little triangle that I'm going to look at here maybe has a side delta S and a side delta S right here. And both of these angles are at 45 degrees. When it stretches out, the lengths of the sides of that triangle change. Now we know that the strain is the change in length divided by the initial length. So if I rearrange this, I can say that the change in length is equal to the strain times the initial length. And since the final length is equal to the initial plus the change in length, I can also say the final length then is going to be 1 plus the strain times the original length. So the new length of this triangle, it stretches out in the x direction. It's going to be the distance delta S times 1 plus epsilon x. And on this side, it's going to be delta S 1 plus epsilon y. Now these 45-degree angles change to be something different than 45 degrees. Those angles open up a little bit, and the value of the angle is going to be 45 degrees plus the shearing strain divided by 2. Okay. So the shearing strain is the change from 90 degrees, since we're looking at a 45-degree angle, and the change from it, we get half as much on each of these. We'll get gamma over 2. So let's label these. This is before it's loaded. And over here, this is after it's loaded. All right. Now we're going to do a little bit of manipulation, a little bit of algebra. Well, let's look at the tangent of the angle after it's loaded. So we're going to look at the tangent of 45 degrees plus gamma over 2. Okay, so it's either this angle or this angle. If we look at this one on the left, we know that we can write the tangent as the opposite over the adjacent side. So that's delta S 1 plus epsilon x divided by delta S 1 plus epsilon y. The delta S's will cancel out, so it doesn't really matter how big our square is. That angle, the tangent of that angle, is going to be given by 1 plus epsilon x divided by 1 plus epsilon y. Now there's a formula in trig that deals with the tangent of two angles that are added together. We can expand this out a little bit and rewrite this. It's the tangent of the first angle plus the tangent of the second angle divided by 1 minus the tangent of the first angle times the tangent of the second angle. We can do a little bit of simplification on this. The tangent of 45 degrees is 1, so this becomes 1 plus, well, the tangent of gamma over 2 is approximately equal to gamma over 2 if gamma is a very small number expressed in radians. So I'm going to write this as approximately 1 plus gamma over 2 divided by 1 minus gamma over 2. And that's equal to what we have over here on this right-hand side, then approximately so. We'll talk about the assumptions again in a moment. 1 plus epsilon x divided by 1 plus epsilon y. On the right-hand side, let's get rid of this 2 on the bottom of the gamma term. We'll multiply the top and bottom by 2. And so we'll get 2 plus gamma divided by 2 minus gamma. All right, so doing a little bit of algebra. Now on the right-hand side of this, then on the top, I have 1 plus epsilon x. And on the bottom, because of the Poisson ratio relation and the fact that we have a uniaxial stress state, I'm going to rewrite this as 1 minus nu epsilon x, Poisson's ratio. I'm going to cross multiply these terms. Let's see, 2 plus gamma, 1 minus nu epsilon x. On the right-hand side, 2 minus gamma, 1 plus epsilon x. Let me pause this and I'll make a little bit more room. And we're simply going to expand these terms out algebraically. So on the left-hand side, we've got 2 minus 2 nu epsilon x. We have plus gamma minus nu gamma epsilon x. On the right-hand side, we have 2 plus 2 epsilon x minus gamma epsilon x. All right, so we're going to collect terms. See, the 2 will cancel out on each side. I have a gamma and a gamma over here. That gives me 2 gamma. Take care of those. We have, in addition to that, some terms that have epsilon x in them. And that would just be this term right here, minus 2 epsilon x. I move it to the other side, put a little check by that one. And I have here a minus 2 epsilon x times nu. I'll bring this to the other side. I've got a plus gamma epsilon x and a minus nu gamma epsilon x equal to 0. All right, now here's something that we need to talk about a little bit too. For engineering materials that we deal with, we typically have very small strains. That's how we made the tangent gamma approximation. If we do have very small strains, we're talking about something much less than 1. Even 0.01 would work, but 1 times 10 to the minus 3 to 1 times 10 to the minus 6 is a typical engineering strain range. Then if we multiply two very small numbers together, like gamma and epsilon x, those will be approximately 0. So another restriction that we can put on using our formula that we talked about, G is equal to E over 2 divided by 1 plus nu, is that in addition to having isotropic material, we also have small strain conditions. All right, well, let's group this a little bit. We have a 2 gamma. I'm going to factor out a minus 2 epsilon x from both of those terms, and I'll have 1 plus nu. At 45 degrees, we know that we have a shearing stress on an inclined plane, tau, that is equal to the axial stress divided by 2. We also know that tau is equal to G gamma by Hooke's law in shear, and that by uniaxial Hooke's law, sigma is equal to E epsilon x, sigma x being the axial stress. So I'm going to replace some of these terms. Instead of having gamma, I'm going to have tau over G. Over on the right-hand side, I have 2 epsilon x, but that's 2 sigma x over E times the quantity 1 plus nu. At 45 degrees, tau is equal to, well, I guess we cancel out those 2's. Tau is equal to sigma x over 2. The sigma x's cancel out, and if we rearrange this, solving for the shear modulus G, we get G equal to E over 2 divided by 1 plus nu. So again, isotropic material and small strains. All right, and that'll wrap this up.